Hello everyone. In this video, I will explain the roll center part 8. The main contents will be the suspension and axle roll stiffness. In this video, I will first explain how the positions of the sprung center of mass and unsprung center of mass relate to the position of the total center of mass, and then I will explain how to calculate the horizontal and vertical positions of the sprung center of mass. Based on the vehicle roll center obtained in the previous video E0075, roll center part 7, I will explain how to calculate the roll angle, roll stiffness, and roll moment caused by the various components of the front and rear suspension, such as the springs and anti-roll bars, and when to consider the effects of tires. Next, I will explain the roll gradient. I have a quiz for you. Which of the following is the wrong expression for roll stiffness? First, the suspension roll stiffness and the axle roll stiffness are connected in parallel with each other, and when they are added together, they become the total ride roll stiffness of the corresponding axle. Second, the suspension roll stiffness and the axle roll stiffness are connected in series with each other, and when their reciprocals are added together, they become the reciprocal of the total ride roll stiffness of the corresponding axle. Third, the spring roll stiffness and the anti-roll bar stiffness are connected in parallel. Fourth, the suspension roll stiffness is the rate of change of the suspension roll moment with respect to the suspension roll angle. Please choose one wrong expression among these. The forces that I want to explain in this video are the forces related to load transfer distribution. In the last video, E0075, roll center part 7, we derived two equations for the front and rear wheels, and we understood that the 6 numbered items are the 6 load transfer elements. In these equations 1 and 4 are the load transfer due to the moment generated by the sprung mass about the roll center. Equations 2 and 5 are the load transfer due to the lateral force acting horizontally on the roll center due to the sprung mass. And equations 3 and 6 are the load transfer due to the unsprung mass. The load transfer elements relevant to this video are elements 1 and 4, which are the load transfer due to the moment generated by the sprung mass about the wheel roll center. These load transfers of the front and rear axles depend on the ratio of the stiffness K phi F of the front axle suspension and the stiffness K phi R of the rear axle suspension. Here and on the next slide, I've listed the physical quantity symbols used in the equations used in this video. The first row lists the types of mass, the second row lists the types of weight, the third row lists each center of gravity location, the fourth row lists the types of longitudinal vehicle length, and the fifth row lists the types of transverse length. The sixth row lists the full names of some abbreviations I think are necessary. M stands for mass, W stands for weight, H stands for height, L stands for longitudinal length, and T stands for transverse length. The subscript S stands for sprung mass or sprung weight, and U stands for unsprung mass or weight. P stands for spring, and B stands for anti-roll bar. The physical quantity symbols shown here are motion ratio, angle, roll gradient, roll stiffness, and stiffness. These relate to the characteristics of the spring, anti-roll bar, and tire. The symbol name Rm represents the motion ratio. For example, RMPF represents the motion ratio of the front axle spring. Phi represents the roll angle. For example, Phi PF represents the roll angle for the front axle spring. R phi represents the roll gradient. For example, R phi PF represents the roll gradient for the front axle spring. The subscript P represents the spring. For example, K phi PF represents the roll stiffness for the front axle spring. B represents the anti-roll bar. For example, K phi BF represents the roll stiffness for the front axle anti-roll bar. And T represents the tire or axle. For example, K phi T is the axle roll stiffness, and K phi TF is the front axle roll stiffness. In order to obtain the moment and load transfer caused by the rolling motion of the sprung mass, we need to find the location of the center of gravity of the sprung mass. The figure here shows a top view of the vehicle. The front of the vehicle is on the left and the rear of the vehicle is on the right. The location of the center of gravity of the sprung mass can be expressed using the coordinates of the center of gravity of the entire vehicle and the center of gravity of the unsprung mass. First, let's find the location of the sprung mass on the horizontal plane. Since the sprung weight is the total vehicle weight minus the unsprung weight, it can be expressed as in equation 1. Meanwhile, the unsprung mass of the front axle is the sum of the left unsprung mass and the right unsprung mass, so it can be expressed as in equation 2. In the same way, the unsprung mass of the rear axle can be expressed as in equation 3. Next, from the moment equilibrium about the front axle, the moment WLF generated by the entire vehicle weight must be in balance with the moment WSLSF generated by the sprung weight and the moment WURL generated by the unsprung weight, so the moment equilibrium equation in equation 4 can be obtained. If equation 4 is rearranged for the distance LSF from the front axle to the sprung center of gravity, equation 5 can be obtained, and if LSF is subtracted from the total wheelbase L, the distance LSR from the sprung center of gravity to the rear axle can be expressed as in equation 6. In the same way, from the moment equilibrium about the rear axle, the moment WLR generated by the entire weight must be in balance with the moment WSLSR generated by the sprung weight and the moment WUFL generated by the unsprung weight, so the moment equilibrium equation in equation 7 can be obtained. By rearranging equation 7 for the distance from the front axle to the sprung center of gravity, LSR, we can obtain equation 8, and by subtracting LSR from the total wheelbase L, we can express the distance from the sprung center of gravity to the rear axle, LSF, as in equation 9. Next, let's find the lateral position of the sprung weight in the horizontal plane. Since the track lengths of the front and rear axles are generally not very different, for the convenience of explanation, we will use the average value of the front and rear axle tracks as the representative track value of the entire vehicle, as shown in equation 10. In addition, as shown in equations 11 and 12, we will assume that the distribution of the unsprung masses on the left and right sides of the front and rear axles have the same values. The total unsprung mass of the front axle can be expressed by equation 13, and the total unsprung mass of the rear axle can be expressed by equation 14. Next, the moment equilibrium equation for the longitudinal line passing through the centers of the right front and rear tires can be expressed as equation 15. The first term in equation 15, the moment WYT generated by the total vehicle weight, must be in equilibrium with the second term, the moment generated by the sprung weight, WSYS, and the third term, the moment generated by the unsprung weight. By rearranging equation 15 for the vertical distance ys from the longitudinal line passing through the center of the left tire to the center of gravity of the sprung mass, equation 16 can be obtained. This time, let's calculate the location of center of gravity for sprung weight in the side view. Here is a side view of the vehicle. The left side is the front of the vehicle and the right side is the rear of the vehicle. WSF represents the front sprung weight and WSR represents the rear sprung weight. Knowing the sprung weight and its longitudinal position, we can calculate the sprung weight on the front axle and the sprung weight on the rear axle. From the moment equilibrium, the sprung weight WSF acting on the front axle can be expressed as equation 17 using the sprung weight WS, the distance from the sprung center of gravity to the rear axle LSR, and the wheelbase L, and, similarly, the sprung weight WSR acting on the rear axle can be expressed as equation 18 using the sprung weight WS, the distance from the sprung center of gravity to the front axle LSF, and the wheelbase L. From the side view of the vehicle, we can find the height of the sprung center of gravity. we can establish an equilibrium equation for the moments generated by each weight with respect to the horizontal line that meets the tire. Since the moment WHCG generated by the total vehicle weight must be equal to the sum of the moment generated by the sprung mass, WSHSCG, the moment generated by the front axle unsprung mass, WUFHUCGF, and the moment generated by the rear axle unsprung mass, WURHUCGR, we can obtain equation 19. Rearranging equation 19 for the height of the sprung center of gravity, HSCG, we can obtain equation 20. This time, we will calculate the sprung weight roll moment arm length. The distance, h, from the roll center height RC to the sprung center of gravity, ms, is that moment arm length. As explained in the previous video, E0075, roll center part 7, the distance h is the moment arm generated by the sprung mass, ms, when it experiences lateral acceleration. The distance h can be found using equation 21. The figure on the left simply shows only the necessary numbers to explain equation 21. Please note that the sizes and shapes of the triangles are different from those in the figure on the right for easy explanation. As shown in the figure, the distance h between the roll center RC and the sprung center of gravity ms is the value obtained by subtracting HRCF from the sprung center of gravity height, HSCG, and then subtracting the length indicated by number 3 in the figure. This can be expressed by equation 21. The third term of equation 21 is the length represented by number 3 in the figure, and can be found using the similarity between the triangle formed by triangles RCF, RC, and point P, and the triangle formed by RCF, RCR, and point Q. The height of the first triangle, the height of the triangle from RC to P, is proportional to the horizontal distance that point P is from point RCF. When point P is a distance L from point RCF, point P coincides with point Q, and the height of the triangle is HRCR minus HRCF, which corresponds to the numerator of the third term fraction in equation 21. Therefore, the length from point P to RC, represented by 3, can be expressed as the third term in equation 21. Finally, the height h is the sprung center of gravity height HSCG minus the front roll center height HRCF, and then the length 3 is subtracted from here, so it can be expressed as in equation 21. Let's first look at the overall overview of roll stiffness. Roll stiffness is defined as the change in roll moment with respect to the roll angle. The roll stiffness of a sprung object is largely composed of 3 components. These are the roll stiffness by the spring, the roll stiffness by the anti-roll bar, and finally the roll stiffness by the tire. The spring and the anti-roll bar are the components that connect the suspension link and the sprung object, and the roll stiffness they generate is connected in parallel with each other. The roll stiffness that is the sum of these two is called the suspension roll stiffness. When the load transfer occurs, the inner and outer tire deformations are different, so the axle roll angle is generated by the tire. The suspension roll stiffness and the axle roll stiffness are connected in series with each other. The total roll stiffness that combines all 3 roll stiffnesses is called the ride roll stiffness. In general passenger cars, the axle roll angle can be ignored because the roll stiffness by the tire is relatively much larger than the other 2 stiffness values by more than 8 times. However, in cases where the suspension roll stiffness is large, the size of the suspension roll angle is not much different from the size of the tire roll angle, so the tire roll angle cannot be ignored. In this case, the tire roll angle must be considered when analyzing the roll of a sprung object. The maximum roll angle that a tire can generate is usually between 1 and 2 degrees. Let's calculate the moment due to the spring. In general passenger cars, what is important in vehicle dynamics is the force acting on the tire road contact area. When suspension components, such as springs, anti-roll bars, and dampers work, the forces generated by them occur at the locations where these suspension components are mounted, and these forces are ultimately transmitted to the contact surface between the road and the tire. Therefore, in order to calculate the lateral load transfer distribution of the vehicle generated by these suspension components, the forces generated by these suspension components must be converted into forces generated by the wheels. If the left spring stiffness is kPl and the right spring stiffness is kpr, and if the left and right spring stiffnesses are the same and the spring stiffness is kp, these relationships can be expressed as equation 22. If the wheel rate is calculated by the spring rate, equation 23 can be obtained. Here, Rmp is the motion ratio for the spring and Kwp is the wheel rate for the spring. If the reaction moment Mp due to the spring is calculated by the wheel rate Kwp, equation 24 can be obtained, and if equation 24 is rearranged, equation 25 can be obtained. Let's see how equation 25 was derived. How can we derive the equation 25? Here is a simple illustration of the deformation of the vehicle spring when the sprung mass rolls. The upper figure is before deformation and the lower figure is after deformation. Phi s is the roll angle of the sprung mass. For the roll angle phi s, the spring deformation length delta L can be expressed as equation 26 by multiplying half the track length by the roll angle phi s. As shown in the figure, the length of one spring decreases and the length of the other spring increases, depending on the roll of the sprung mass. Accordingly, a couple force Fp is generated on the road surface. The couple force Fp can be expressed as equation 27 using the wheel rate Kwp. Continuing, the moment Mp generated by the couple force Fp can be expressed as equation 28. By substituting the spring deformation delta L of equation 26 into equation 27 and substituting the couple force Fp of equation 27 into equation 28. The moment Mp can be obtained as in equation 29. Let's find the roll stiffness from the wheel rate of the independent suspension. The reaction moment for the spring can be calculated separately for the front and rear axles. For the front suspension, the reaction moment of the front axle spring, MPF, can be expressed as equation 30 using the wheel rate of the front spring, KWPF. Similarly, for the rear suspension, the reaction moment of the rear spring, MPR, can be expressed as equation 31 using the wheel rate of the rear spring, KWPR. Therefore, the reaction moment due to the spring acting on the entire vehicle can be expressed by adding these two, as equation 32. If phi s is small, and the track width of the entire vehicle is the same for the front and rear wheels, as shown in equation 33, the moment Mp acting on the entire vehicle due to the spring can be expressed as equation 34. If the front and rear tracks are different, their average value, as shown in equation 10, is used as an approximation. In equation 34, Kwp is the sum of the front wheel rate and the rear wheel rate, as shown in equation 35. Roll stiffness represents the rate of change in roll moment with respect to the roll angle. Therefore, the roll stiffness K phi Pf for the front spring can be obtained using the previously obtained equation 30, as shown in equation 36. The unit of the roll stiffness K phi Pf of the front spring, expressed in equation 36, is Newton meters per radians. Equation 37 gives the roll stiffness of the front spring of equation 35 in Newton meters per degree. In the same way, the roll stiffness K phi PR for the rear spring can be obtained as shown in equation 38. Equation 39 gives the roll stiffness of the rear spring of equation 38 in Newton meters per degree. As explained in the previous video, E0075, if there is no torsional deformation of the sprung mass, the roll angle will have the same value on both the front and rear axles. Therefore, the roll angle is the same on both the front and rear axles. Also, since the moment for the entire vehicle spring is the sum of the front wheel moment and the rear wheel moment, as shown in equation 32, the roll stiffness K phi p of the entire vehicle spring can be expressed as equation 40. By substituting equations 33 and 35 into equation 40 and rearranging equation 41, which represents the roll stiffness of the entire vehicle due to the spring, can be obtained. If equation 41 is expressed in Newton meters per degree, it becomes equation 42. This time, we will learn about the stiffness of the anti-roll bar. The figure on the left is an anti-roll bar of an actual vehicle. Here, for the convenience of explanation, we will use a simple model of the anti-roll bar. We will explain the front anti-roll bar as a representative. In the middle figure, the anti-roll bar can be largely divided into three parts based on its function. There are two bending arms, one on each end, and a relatively long torsion element in the middle. The torsion element receives only a torsional force, and its central axis does not change even when the force is applied. When the roll of the sprung mass occurs, the bending arms deform in opposite directions, generating a torsional torque in the torsion element. When generating a torsional torque, the load is transmitted through the bending arms, so bending stress occurs in the two bending arms. Since these three elements are not parallel but connected in series, the overall stiffness value Kb must be calculated using the spring stiffness calculation formula connected in series, as shown in equation 45. The cross-section of the anti-roll bar usually uses a pipe-shaped part with a hollow center. Let the inside diameter of these pipes be Ri and the outside diameter be Ro. In order to calculate the stiffness of the torsion element, the polar moment of inertia J is required, which can be calculated using the inside and outside diameters with equation 43. Also, in order to calculate the stiffness of the bending arm, the second moment of inertia I is required, which can be calculated using the inside and outside diameters with equation 44. Let's first find the stiffness of the bending arm of the anti-roll bar. In order to find the stiffness of the bending arm, when the torsional load is applied due to the rolling motion of the sprung load, we need to know the displacements of points P and Q, located at the ends of the bending arm. As shown in the figure on the left, the two bending arms are perpendicular to the torsion element at both ends of the torsion element. When the roll of the sprung mass occurs, these two bending arms move in opposite directions and generate torsional stress in the torsion element. Therefore, in order to calculate the displacements of points P and Q at the ends of the torsional bending arms of the anti-roll bar, we need to know the bending displacement delta A of bending arm A, the torsion angle of the torsion element LTB, and the bending displacement delta C of bending arm C. Let's find delta A and delta C when the cross-sections of bending arm A and bending arm C are as shown in the figure below on the left. The displacement delta due to the bending load of the bending arm can be obtained from equation 46. In the denominator of this equation, E is Young's modulus and I is the second moment of area. Therefore, the bending stiffness of the bending arm A can be expressed as equation 47. The displacement delta C due to the bending load of the bending arm can also be obtained in the same way as equation 48. Similarly, the bending stiffness KTC of the bending arm C can also be expressed as equation 49. Next, let's find the torsional stiffness of the torsion element of the anti-roll bar. The figure on the right is the side view of the figure on the left. As shown in the figure, when a coupled force F is applied to the end of the bending arm, a torsional torque is generated in the torsion element. Each theta represents the torsion angle, and delta B represents the relative displacement of the bending arm points P and Q. As shown in equation 51, if the lengths of the moment arms LTA and LTC are equal, this can be expressed as LT. The torsional torque acting on the torsion element can be expressed by multiplying the force F by the bending arm length LT, as in equation 52. The polar moment of inertia of the torsion element was obtained using equation 43 above. Using this, the torsion angle theta can be expressed as in equation 53. In equation 53, G is the modulus of rigidity, that is, the shear elastic modulus. Using the angle theta, we can obtain an approximate value for the relative displacement between points P and Q, as in equation 54. From this, the angle theta can be expressed as in equation 55. By substituting theta of equation 55 into equation 53, we can obtain equation 56. By substituting the moment m of equation 52 into equation 56, we can obtain equation 57. Since the stiffness value kTb of the torsion element is the force F divided by the displacement delta B, by rearranging equation 57 for kTb, we can finally obtain the stiffness value kTb of the torsion element, as in equation 58. So far, the stiffness kTA of bending arm A, the stiffness kTb of the torsion element, and the stiffness kTc of the bending arm C can be combined to obtain the overall stiffness kBf of the front anti-roll bar. As explained above, since these three elements are connected in series, not in parallel, the stiffness values should not be added to calculate them, but their reciprocals should be added, as shown in equation 59. By substituting the stiffness kTA of bending arm A obtained using equation 47, the stiffness kTc of bending arm C obtained using equation 49, and the stiffness kTb of the torsion element obtained using equation 58 into equation 59, the overall stiffness kBf of the front anti-roll bar can be obtained. The overall stiffness kBr of the rear anti-roll bar can also be obtained in the same way. Here is a picture of how the roll of the sprung mass in a double A-arm suspension moves the suspension components, including the anti-roll bar. The upper picture is before the sprung mass rolls, and the lower picture is after the sprung mass rolls. The picture on the right is a side view of the anti-roll bar. In a double A-arm, the upper arm is generally designed to be shorter than the lower arm. The reason for this design is that when the sprung mass rolls, as shown in the picture, the displacement of the outer connection point of the upper arm, which connects to the steering knuckle, moving laterally inward, can be greater than the displacement of the outer connection point of the lower arm, which connects to the steering knuckle, moving laterally inward. As a result, the upper part of the tire moves laterally inward and the lower part of the tire moves outward relative to the upper part. Therefore, the camber angle increases in the negative direction. The reason this suspension movement helps with vehicle handling is because it creates a negative camber angle when cornering, which can help with camber thrust that occurs independently of the tire slip angle. Let's find the moment due to the anti-roll bar. Since the total stiffness of the front axle suspension anti-roll bar, kBf, is found using equation 59, the wheel rate due to the front axle anti-roll bar, kWbf, can be found using anti-roll bar stiffness as shown in equation 60. In equation 60, Rmbf represents the motion ratio of the anti-roll bar. The moment Mbf due to the anti-roll bar can be found using equation 29 in the same way that the moment due to the spring was found using equation 29. If the wheel rate, kWp in equation 29 is replaced by the wheel rate of the front anti-roll bar, kWbf, the moment due to the anti-roll bar, Mbf, can be found using equation 61. Next, if equation 61 is rearranged, the final equation 62, for the moment Mbf, due to the front axle anti-roll bar, can be obtained. Since the wheel rate and moment due to the anti-roll bar have been obtained for the front and rear wheels respectively, let's obtain the moment generated by the entire front and rear anti-roll bars. The moment generated by the front anti-roll bar, Mbf, can be expressed by equation 62, and the moment generated by the rear anti-roll bar, MBR, can be expressed by equation 63. If the sum of the moments generated by the front and rear anti-roll bars is added together, the moment generated by the entire anti-roll bar for the entire vehicle can be expressed by equation 64. If the roll angle phi s is small, and the wheel track TW has the same value for the front and rear wheels, the moment generated by the entire vehicle anti-roll bar, MB, can be expressed by equation 65. If the front and rear tracks are different, their average value, as shown in equation 10, is used as an approximation. KWB in equation 65 can be defined as equation 66. In equation 66, KWBF is the wheel rate of the front axle anti-roll bar, and KWBR is the wheel rate of the rear axle anti-roll bar. Since the front and rear axle anti-roll bars are connected in parallel to the sprung mass, the wheel rate of the entire vehicle anti-roll bar, KWB, is the sum of these two, and can be expressed as equation 66. Next, let's find the roll stiffness of the anti-roll bar. The roll stiffness is defined as the change in roll moment with respect to the roll angle. Therefore, the stiffness of the front anti-roll bar can be expressed by the second term of equation 67. If equation 62 is substituted into the second term, the numerator, MBF of equation 67, the third term of equation 67 can be obtained. If this is expressed in degrees, it can be expressed as equation 68. In the same way, the stiffness of the rear anti-roll bar can be expressed by the second term of equation 69. If equation 63 is substituted into the numerator, MBF of the second term of equation 69, the third term of equation 69 can be obtained. If this is expressed in degrees, it can be expressed as equation 70. The roll stiffness of the entire vehicle is defined by the second term of equation 71. The total vehicle moment due to the anti-roll bar, MB, is the sum of the front axle moment, MBF, and the rear axle moment, MBR, so it can be expressed by the third term of equation 71. By substituting equations 62 and 63 into the third term of equation 71, the fourth term of equation 71 can be obtained. If the roll angle phi s is small and the average of the front and rear axle tracks is used as the track of the entire vehicle, the roll stiffness of the anti-roll bar can be expressed by equation 72. In terms of degrees, it can be expressed by equation 73. Now that we have the roll stiffness of the spring and the roll stiffness of the anti-roll bar, let's find the total suspension roll stiffness by combining the two. So far, we have obtained the roll stiffness of the spring for the entire vehicle, K phi p, as in equation 74, and the roll stiffness of the anti-roll bar for the entire vehicle, K phi b, as in equation 75. Since the spring and the anti-roll bar are mounted parallel to the sprung mass, the suspension roll stiffness of the entire vehicle, K phi s, generated by these two can be obtained by simply adding them together, as in equation 76. We can see from equation 76 that the spring roll stiffness, K phi p, expressed in equation 74, and the anti-roll bar roll stiffness, K phi b, expressed in equation 75, become the suspension roll stiffness of the entire vehicle, K phi s. Here's something to keep in mind. If the relative displacement of the left and right wheels with respect to the sprung mass is the same, the roll stiffness of the anti-roll bar is 0. For example, if the left and right wheels double bump at the same height at the same time, the anti-roll bar will not generate any force at all. Continuing, let's review the process of finding the roll gradient for a vehicle traveling at a constant speed over a constant radius. This is taken directly from the previous video E0075 roll center part 7. We start with the equilibrium equation 77 for the roll center RC. Rearranging equation 77 for phi s gives equation 78. Remember that the k phi s in the denominator of the right-hand side of equation 78 is the roll stiffness for the entire vehicle. The expression for the roll angle phi s obtained from equation 78 is used to calculate the load transfer caused by the sprung mass for the front and rear wheels. By definition, the roll angle gradient is the derivative of the roll angle with respect to the lateral acceleration, as shown in the second term of equation 79. So differentiating equation 78 with respect to the lateral acceleration ay gives the roll gradient r phi s, as shown in the last term of equation 79. The roll gradient r phi s is proportional to the sprung mass ms and the height from the roll center to the sprung center of gravity, as shown in equation 79, and is inversely proportional to the suspension roll stiffness minus the rolling moment generated by the sprung mass. The moment arm of the sprung mass about the roll center was obtained in the previous video, E0075, roll center part 7. From the previously obtained equation 79, we can obtain the moment arm h for the moment developed by the sprung mass due to lateral acceleration as a function of the roll gradient. In the figure, h is the distance between the roll center and the sprung center of gravity. The distance h is the moment arm length for the moment developed due to the lateral force caused by the sprung mass. Rearranging equation 79 in terms of the distance h between the roll center and the sprung center of gravity, we obtain equation 80. As shown in equation 80, the distance h from the roll center to the sprung center of gravity can be expressed as a function of the roll gradient r phi s. Let's learn about axle roll stiffness. Axle roll stiffness is determined by the stiffness of the tire. In general, tire stiffness is much larger than the stiffness of the spring or anti-roll bar. Therefore, in general cases where tire deformation is not large, there is no need to consider axle roll stiffness. In general vehicles, the axle roll angle is between 1 and 2 degrees, which is about 1/8 of the suspension roll angle. However, if the suspension roll stiffness is large, the axle roll stiffness must be considered. The left tire stiffness can be expressed as the sum of the front left tire stiffness and the rear left tire stiffness, as in equation 81. Similarly, the right tire stiffness can be expressed as the sum of the front right tire stiffness and the rear right tire stiffness, as in equation 82. As shown in equation 33b, if phi t is small, the left tire stiffness and the right tire stiffness are equal, and the front axle track and the rear axle track are equal, the rolling moment, ms, can be expressed as in equation 83. From the definition of axle roll stiffness, k phi t can be expressed as the second term of equation 84, and by substituting ms of equation 83 into the second term of equation 84, the third expression of equation 84 can be obtained. Equation 84 can be expressed in units of angle as equation 85. Ride roll stiffness means a value that includes both suspension roll stiffness and axle roll stiffness. Here, the suspension roll angle and axle roll angle are shown together. The axle roll angle phi t is the roll angle that occurs due to tire deformation, and the suspension roll angle phi s is the roll angle that occurs related to the spring and anti-roll bar. The angle phi that adds up these two angles is the final roll angle of the vehicle. The total roll angle phi calculated here will be called the ride roll angle. The suspension roll stiffness k phi s is obtained by equation 76, and the axle roll stiffness k phi t is obtained by equation 84. As shown in the figure, the suspension roll stiffness k phi s and the axle roll stiffness k phi t are connected in series, not in parallel. Therefore, in order to obtain the ride roll stiffness k phi r that reflects both roll stiffnesses, the serially connected stiffness equation 86 must be used. If the fractional equation of equation 86 is solved for k phi r, equation 87 can be obtained. This figure is shown to explain the twist and roll angle of the sprung object. The red and blue lines are reference lines. The red line is attached to the front end of the sprung object, and the blue line is attached to the rear end of the sprung object. The figure on the upper side is the case where the sprung object does not twist, and the figure on the lower side is the case where the sprung object twists. As shown in the figure of section AA of the upper side, when the sprung object does not twist, the front axle roll angle phi f and the rear axle roll angle phi r of the sprung object are equal to each other. When the suspension stiffness is large and tire deformation must be considered, the roll angle of the sprung object on the front axle can be expressed by adding the roll angle of the front suspension and the front axle roll angle, as in equation 88. In the same way, the roll angle of the sprung object on the rear axle can be expressed by equation 89. If there is no twist in the sprung mass, the roll angle of the sprung mass should be the same at the rear axle as at the front wheel, which can be expressed as in equation 90. Also, the overall roll angle of the sprung mass can be expressed by the suspension roll angle phi s and the axle roll angle phi t, as shown in equation 91. When twist occurs in the sprung mass, the roll angles at the front and rear axles are different, as shown in equation 92. The lower figure shows the case where twist occurs and the sprung mass experiences a twist angle, theta s. As shown in the figure, due to the twist of the sprung mass, the rear roll angle phi r is less than the front roll angle phi f. In this case, the difference between the front roll angle phi f and the rear roll angle phi r is the twist angle of the sprung mass, as shown in equation 93. Let's look at the ride-roll gradient considering tire deformation. The roll gradient is the rate of change of the roll angle phi with respect to the lateral acceleration ay and can be expressed as in equation 94. The figure on the left shows the suspension roll angle and the axle roll angle together. The overall roll angle phi is the sum of these suspension roll angles and the axle roll angle. The overall vehicle roll gradient can also be expressed as equation 95 by summing the suspension roll gradient and the axle roll gradient. In equation 95, r phi s represents the suspension roll gradient and r phi t represents the axle roll gradient. The suspension roll gradient r phi s can be expressed as in equation 96 using the suspension roll angle phi s, and the axle gradient r phi t can be expressed as in equation 97 using the axle roll angle phi t. As explained above, the axle roll angle and axle gradient are generally much smaller than the suspension roll angle and suspension gradient and can be ignored, but the axle roll angle should not be ignored because a large suspension roll stiffness reduces the difference between the suspension roll angle and the axle roll angle. Let's take a quiz. Which of the following is the wrong expression for roll stiffness? First, the suspension roll stiffness and the axle roll stiffness are connected in series, not in parallel, and the sum of their reciprocals is the reciprocal of the ride roll stiffness. Therefore, number 1 is incorrect. Second, the suspension roll stiffness and the axle roll stiffness are connected in series with each other, and when their reciprocals are added together, they become the reciprocal of the total ride roll stiffness of the corresponding axle. Third, the spring roll stiffness and the anti-roll bar stiffness are connected in parallel. Fourth, the suspension roll stiffness is the rate of change of the suspension roll moment with respect to the suspension roll angle. Therefore, number 1 is incorrect. Let's summarize the content of this video. The factors related to the sprung center of gravity location are, in relation to the longitudinal position, the overall vehicle weight and longitudinal center of gravity location, sprung weight, unsprung weight, and wheelbase. In relation to the lateral position, the overall vehicle weight and lateral center of gravity location, sprung weight, unsprung weight, and wheel track. In the rolling motion of a sprung body, the suspension roll angle is the cross-sectional rotation angle of the sprung mass that the lateral acceleration acts on the sprung mass about the roll center, and is equal to the moment that the sprung mass generates about the roll center divided by the suspension roll stiffness. The axle roll angle is caused by the difference in the vertical positions of the left and right wheel centers due to tire deformation when the vertical load on the left and right tires changes due to lateral acceleration. In a general vehicle, the axle roll angle is about 1/8 of the suspension roll angle, and the maximum value is in the range of 1 degree to 2 degrees. When the axle roll angle is relatively small compared to the suspension roll angle, such as in a general vehicle, it can be ignored. When the suspension roll stiffness is large and the suspension roll angle becomes close to the axle roll angle, the axle roll angle should be considered. Roll stiffness is explained. There are three main roll stiffness elements of a sprung object. Suspension roll stiffness includes roll stiffness by spring and roll stiffness by anti-roll bar, and an axle roll stiffness generated by the tire. Looking at the relationship between the roll stiffnesses, the spring roll stiffness and the anti-roll bar roll stiffness are connected in parallel, and the suspension roll stiffness and the axle roll stiffness are connected in series. The suspension roll stiffness represents the amount of change in the suspension roll moment for the suspension roll angle, and the ride roll stiffness represents the overall roll stiffness that combines all of the above three roll stiffnesses. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0074 is the sixth part of the vehicle roll center series, which looks at how the gyroscopic effects of rotating vehicle components affect handling. We look at torque steer due to gyroscopic effects on bumps and rebounds, and how the rotation of engine components and vehicle wheels affect handling when the vehicle turns. In the latest video, E0075, the seventh part of vehicle roll center, we looked into 6 lateral load transfer elements caused by lateral acceleration and knew only the moment caused by sprung mass affects the load transfer distribution due to front and rear suspension stiffnesses. Also, we learned the process to calculate the lateral load transfer and weight distribution. The next video is Roll Center Part 9, looking at how the roll stiffness ratio of the front and rear axles affects load transfer and how that affects handling performance. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye, guys.